Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 1, the electromagnetic spectrum, which I am dedicating to James Maxwell. James Maxwell is not my videographer. James Maxwell was a Scottish scientist and mathematician in the 1800s who discovered that in addition to the light that he could see and the infrared heat that he could feel, there was a lot of other radiation around him that mankind at that time could neither detect nor create. So he got other scientists started in looking for these other types of radiation. The Curies, for example, investigated X-rays. So the electromagnetic spectrum starts on the left with radio waves, slightly cut off, but you get the idea. And radio waves are measured in meters. Next, we have the infrared rays. Next is visible light. Then ultraviolet. X-rays. Gamma rays. And cosmic rays. Cosmic rays are so small they're measured in nanometers, 10 to the minus 9 nanometers. And 1 nanometer is defined as 10 to the minus 9 meters. So you can imagine how small cosmic rays are. So the mnemonic that I use is Rivux GC for these different types of radiations. You can think of it as the latest electric vehicle running on green current. Visible light, the mnemonic is Roy G Biv. Roy, red, orange, yellow, green, blue, indigo, violet. Each of these colors has a different wavelength ranging from 760 nanometers for red to 400 nanometers for violet. So as we go from left to right, there's increasing frequency of the rays. And you can use a mnemonic if. And if the frequency increases, there's decreasing wavelength as we go from left to right. We abbreviate wavelength with the Greek letter lambda. And the speed of light is equal to, or the speed of any of the waves is equal to the wavelength times the frequency. The speed of light and all these other waves in a vacuum is actually 299,792,458 meters per second. They're about 90,000 meters per second less in air than in a vacuum. So we round up for both air and vacuum wave speed to 3 times 10 to the 8th meters per second. Now let's draw some waves. There's a wave, there's a wave. That didn't work. You can tell that art was not my best subject in school. All right, that's better. So these are 3 waves. A wavelength, one wavelength is defined as a distance between corresponding points on successive waves. So in this case, the beginning of each hill from one to the other, that's a wavelength. So we have 3 wavelengths in this time interval. Let's say, for argument's sake, it's a 1-second time interval. So we have 3 cycles per second. We abbreviate cycles per second as hertz, which is abbreviated Hz. Now, let's see what happens when we make the wavelengths half as long as they were in the black section. So now, if we count, instead of having 3 wavelengths in 1 second, we have 6 wavelengths in 1 second. or 6 hertz. So when you double the wavelength, you have the frequency, and vice versa. If you double the frequency, you have the wavelength. If you're wondering where microwaves are, they're right here between radio and infrared. So while you're eating your microwave popcorn while watching this video, please thank James Maxwell. So as light travels in waves, it can vibrate in different directions. The waves can vibrate up and down, or they can vibrate left and right, or they can vibrate diagonally in that direction, or they can vibrate diagonally in that direction, or actually the light waves can vibrate in any of the infinite directions around the clock dial. So I have here 2 polarizing filters. A polarizing filter allows light through that vibrates in only one direction. So if the 2 filters allow light through that vibrates in the same direction, you get the maximum amount of light that passes through them. But as I rotate one filter with respect to the other, less and less light passes through until they're 90 degrees out of phase. So let's say the filter in front lets light through that vibrates only up and down, and the filter in back lets light through that vibrates only left and right. You get 0 light transmission. And then again, as I rotate them back to the way they were before, more and more light goes through. This is further proof of the wave nature of light.